Hi everyone, my name is Lars Albertsson. I work as a data architect at Schibsted Media Group. And I observed that I've had a career that is more and more directed toward counting things, counting lots of things. Chat messages, money, songs played, and so forth. And now I'm counting things displayed on Blocket and Aftonbladet and so forth. At some point, not too long ago, I saw an internal blog statement that looked something like this, that we had lots of things and we sort of promised to count them live. But since that's not possible, we looked at like historical numbers and then extrapolated. And I was a bit shocked at the statement of that is not possible. And I sort of realized that there are some number of techniques that are not too widely known. This is actually not hard to do. So I was inspired by another talk and decided to put together a talk and sort of display that counting things, lots of things in real time is actually not hard. You can do it with a, you don't need to be a PhD in algorithms or anything. So this is a little like technical talk on how to do these things. Please dive in and ask questions while I'm talking in case I'm confusing things. The sort of success of Hadoop has sort of led to the expectations that if you have to count lots and lots of things, more than fit in a machine, you have to wait for like minutes or hours. It's some kind of parallel to the 90s where the success of Windows made people assume that computers crash every 30 minutes or something. You don't need Hadoop to do these things. It's much simpler. You can actually set up a system that does very accurate counting, even at a large scale, without too much effort, as long as you have like scalable collection of the things that you count and a scalable bus to publish everything, and a scalable way to bucket the things you want to count. Typically, you want to bucket in like time windows or geolocations or age, or something. This is straightforward. You need a bunch of machines. You need a bit of plumbing. In most cases, you don't need to like make it this complicated and go this far. Because in many cases, you do not need an exact count. It is often sort of a trade-off between exact a bit later or with a bit more work, or a rough count right now, right away. So if you have a hypothetical scenario that you have a second-hand stuff site, such as Blocket, where users search for things, and you're operating a looking for dinner site, such as Allt om Stockholm, if you're quick and react to the actions of the users in the last few seconds or minutes, then you can actually respond quickly with better recommendations and say, oh, you're looking for dinner and you like violins. Here's a violin concert for you. It all boils down to three different basic types of approximate counting. If you learn to sort of master these three types, then you can build sort of more complex operations on top of these. And the three different types are cardinality, how many different items were counted were observed in a time window. What are the most popular items, and how many items of how many occurrences of item Y was seen in the last few minutes. Based on these operations, if you master these, you can build stuff like personalization and recommendation algorithms. So I will go through them, and then I'll show a brief example of how these can be one of these can be used to build a recommendation structure. So if you want to count cardinality, your first naive approach would be to use a Java hash set. That's the sort of most straightforward implementation of cardinality count. If you do, you pay a high overhead. It's I think 400 bits per item is probably in the low range. It's in practice a lot more than that. If you count lots of things or in many time windows, that will be too much. A hash set is actually a hash vector plus a linked list. So if you think very little, you realize that you can cheat a bit and skip the linked list and just have the hash vector. And then you can choose the size of the hashes to be 16 bits, 32 bits, whatever you want, and trade sort of space for accuracy. This will get you quite far. And then you realized you've heard of some other approximate implementation of set. It's called a Bloom filter. So let's see if we can use that one instead. And the way a Bloom filter works is that you have a bit vector. You choose the size of the bit vector, trading off space for accuracy. And then you have a number of hash functions for the item that you put in. And you put your item through the hash functions, and the result points out a few slots in the bit vector. And when you insert things, you set all of these slots to 1. Then when you do read operation to see is this particular item in the Bloom filter, you read all of the corresponding slots that correspond to these hash functions. If all of them are 1, you say, oh, yes, it has probably been inserted. You might be wrong, you might get a false positive, but if one of them is 0, you know it hasn't been inserted. But in order to count things, then you keep a Bloom filter to see, have I seen this item before? Yes, okay. Next one. If you haven't seen this item before, you increment a counter. And then you have made a very simple cardinality counter with a Bloom filter. Now, that is a problematic representation, because if you look at a wider context, you do not want to count the number of different items that you have seen since the dawn of time. You actually typically want to count the number of items that you've seen in the last minute or last hour or last day or something. And in practice, you would count for a time quantum and then sort of save that count and then start a new time quantum, save that count and so forth. And you want to compare with previous counts to see what has changed and so forth. And as time goes by, you probably want to aggregate the old counts. And in order to do this aggregation, you need a monoid representation. A representation where the different time buckets can be added easily. Also, since you want to count lots of windows, space matters here. You typically cannot afford to spend hundreds of megabytes for each time window, because then they won't, very few time windows will fit into your machine. Going back to the monoid, the Bloom filter plus counter is not a monoid. So let's see if we can improve it a little bit to make a monoid implementation. The Bloom filter led us to a bitmap. So one also slight simple approximation of cardinality counter is to take the value that you put in, you hash and toggle or set a point, a slot in the bitmap to 1. And then you just count the number of bits in your bitmap. Whenever there are collisions, you will undercount. But if the bitmap is large enough, you will get a decent count. But then you realize, I will get a slight undercount. Perhaps I can estimate how much I undercount and sort of compensate for that. And then you've done so much thinking that you can actually call it a linear probabilistic counter and publish a paper about it, which somebody did. And there are open source implementations of this as well. That might have led you to the idea to read other papers, and then you stumble on something called the hyper-log-log counter, which I will not attempt to explain. And if you look at numbers, the first line here is your naive Java hash set implementations. In this particular case, counting the vocabulary size of Shakespeare's complete works requires, 10 megabytes. The linear probabilistic counter requires a few kilobytes, and the hyperlog-log compresses it even more. The guys that presented the hyperlog-log paper claims they can count a cardinality of 1 billion items with 2% error in just a few kilobytes. So it's an amazing compression factor here. This is not only relevant for counting things in real time. This is also relevant for storage, right? If you store things that map to something to cardinality, you can actually use this approximate representation to store things. So that was cardinality. Next thing we should try to get right is the most popular items. In general, when you count the the frequency of the most popular items, you only care about the real popular ones. And now I'm taking the example of songs, since I used to work at Spotify. I'm used to counting songs, or in this case, actually artists. You care about the most popular artists. You typically do not care about the less popular artists, such as Pep's Passion, because frankly, nobody really listens to them except for a few people. So there is a very simple thing you can do. You have your sorted table of the most popular artists. And next song comes by, you look at the artist, it's U2, we increment that by 1. And then eventually somebody actually listens to Peps, but he's not in the table. So what do? You take the bottom item in the table, which happens to be Dolly Parton in this case, who's not super popular either in Sweden. And you assume that Peps has the same count as Dolly. It's probably a little high. Fine, we assume that. So we increment by 1, and we give him 185. And then Dolly comes by. But now we've lost count of Dolly. So we assume that she has the same count as Peps, and she gets 186. And what will happen here is that the artists that are in the bottom here, that go in and out of this top K table, they will be overcounted. Whereas the artists in the top, assuming this one is actually longer than 5 items, will actually get a pretty accurate count. Now, if you think back to the context with the time windows, when you start a new time window, this one will be empty. So if you want to get a less overcounting, you can weight the sorting here based on earlier time windows, and you will do better. I'll leave that as an exercise for the audience. So that was two, cardinality and top K counting. And the last sort of...
Excuse me.
Yes.
For the top K, if you want to show K, how long is your actual list then?
A good ballpark number is perhaps 10K, but it depends on the distribution of your data stream. So in the case of songs, you might have different types of songs earlier in the day than late in the day. So if you have a swing here, you need to sort of make up for that, right? So it all depends on your data. Everything approximate depends on your data. That's the simple answer. Okay, so now the third sort of approximate counting primitive is the approximate map. Get me roughly the number of items of, or the number of occurrences of item I. And in this case, it often turns out to be that it's better to overcount than to undercount. Or at least it's better to miscount in just one direction. So there's something called a count min sketch that will do an approximate map with overcounting. In this case, you have a matrix, and whenever you get an item and you are adding 1 to the item, you apply a number of hash functions, 1 hash function for each row. And then the output of these hash functions point out a specific column. And you increment in each row, the slot pointed to by this column in the row. Is this clear? Excellent. And then when you want to read out the value of your item Y here, you do the same hash function that points out the different slots. And then you take the minimum of the values in these slots. In this case, it would be 3. Then you know that this particular item has cannot have been incremented more than 3 times. It might have been incremented less if you get collisions, but never more. Okay, fair enough. Now we can refine, if we want to, we can refine the top K implementation here. And when things drop off at the end of the table, when you're inserting them again, you can actually do a lookup in a count min sketch. So in this case, the term used is called, the top K is called a heavy hitters list. And And so in this example, when peps come by, you discard Dolly's number, you look up peps in your count min sketch, it's played 13 times, and when Dolly comes by, you throw peps out again, and you actually look up an accurate number, hopefully accurate number for Dolly. In this case, you will do some overcounting. It will be more spread out than in the previous top K implementation. But you have a less risk of the overcounting is smaller. So it is often the case that you do not only want to count the top artists globally, but you also want to count the top artists in Sweden or the top artists in a specific age group. And you can, if you increase the size of your count min sketch a bit, you can actually dump all of the different variations in there. So let's say somebody my age in Sweden plays a U2 song. Then you, instead of just having U2 as the key, you create a key from the tuple of Sweden, 31 to 40, and U2. And you hash that key in increment 1. And you also do it for any country, 3140, U2, and Sweden, any age, U2, and any country, any age, U2. And when you want to retrieve values, you just apply the same function to the keys. Now, if you want to do top K with heavy hitters, then you actually need multiple different top K lists for different age groups and for different geo groups and so forth. So this only scales to a few dimensions, but that might be good enough for you. You can also, the heavy hitters will have, in this case, will have a lot of common items. So you can probably do clever heuristics to save some space by ignoring the common items. That's also left as the dreaded exercise for the audience. All right, how do you actually stitch this together? What kind of sort of infrastructure machinery do you need? If you do this, the simple ones that are showed, like the CMS or the top K or something, a typical machine can process on the order of somewhere in the order of 10,000 messages per second, and the data structures are typically small and fit into memory. And that happens to be the same order of magnitude as the songs played on Spotify on average. So unless you have heavier traffic than Spotify, you probably only need one machine or a few machines. If not, this maps well to a parallel real-time computation infrastructure such as Storm, because all of these are monoids and they can be like counted and aggregated in parallel. You can have a count min sketch structure on one machine, each machine, and then Storm will provide like a good, nice aggregations function for you, and you can just add these CMSs. And my advice, if you start out to do this, is to connect it to the rest of your system via a pub/sub channel, because then it becomes sort of loosely coupled. If you use something like Kafka for pub/sub, Kafka also contains history, which means that you don't need to keep up all the time. If your counting goes down or out of memory or whatever, you can restart it later and it will catch up and then publish the results to Kafka for other people to consume. This actually makes a very simple and nice way to integrate approximate things like this, because you don't want to depend too deeply on them. There's an option here. If you have more dimensions than just geo and age, that's sort of a brute force approach. You can build an Elasticsearch cluster and store every single message in there. That requires a lot more storage, but Elasticsearch happens to be fairly nicely scalable. And Elasticsearch is really good at counting things. I haven't really figured out how it does it, but it turns out that these queries, like most popular per age and geo, it handles them really well. And we actually made some Hack Week projects at Spotify with doing this type of counting with both approaches. And the Elasticsearch guys were a lot faster in actually bringing something working up, but it required a cluster rather than one machine. Okay, so counting is great. How does this map to something that actually provides business value, such as recommendations? I'm not going to give you a deep lecture on recommendations. One of the popular base techniques is called collaborative filtering, where you sort of build a matrix with users and items, and then you find similar columns in the users row and look that, and perhaps an algorithm would deduce that users C and F are similar in terms that they both like P and Q equally much. And therefore, we could recommend that user number F should try item R and user C should try item S. It becomes a little contrived in this like small example, but that's the sort of the basis for collaborative filtering. Now, in an AV representation, the users times items can grow really big. Spotify, we had 50 million users, and we had some on the order of 20 million different songs. Big matrix. So what you can do instead is make an approximate representation of this matrix. You start by flipping it so that you, instead of storing the matrix in a natural manner, you store the coordinates and the numbers. And then you sort it, instead of sorting it by coordinates, you sort it by the values, so you get the highest values on top. Then you can use your top K or top K via count min sketch to sort of cut the bottom end and cut all the low values. And now you have a much more compact representation of your matrix, where all the low values are essentially represented by zeros. So you keep this representation on your far right in memory instead of the full matrix. And this one happens to be just as good for recommendations, because in terms of recommendations, it's actually the high values that count in the recommendation algorithms. Does this make sense? Excellent, excellent. That's about it. If you want to go into more depth and know more about this from people that work closely with it, I was very inspired by the top talk by Mickey O'Brien on Berlin Buzzwords last year. And also Ted Dunning, that works at MapR, has some very interesting talks on how to do like real-time processing for more complicated in more complicated deep learning scenarios for like anomaly detection in real time, and for example detecting out of rhythm heartbeats and so forth. There are a couple of good open source implementations, and there's one in Java called Streamlib that has count min sketch and cardinality count and so forth. And Twitter, as always, is a good source for good open source stuff. They have a library in Scala called Algebird, which has a bunch of these things, like CMS with heavy hitters, for example. Questions?
On the machinery, have you tried Hadoop and Spark? Popular in this area?
Yes, I have. I have not worked, I should say, professionally with it. It is in use in Spotify. It is most of Spotify uses Hadoop for batch computations and Storm for real-time computations. But there are a couple of functions using a Spark cluster. For batch, it seems to work quite well. Spark streaming, I've tried a bit. That is not yet mature enough, unfortunately, because it would be very nice to be able to share code between batch and streaming in a nice way. So at Schibsted, our current direction is to use Spark, but we haven't got it up and running yet.
I was thinking about recommendations. I read a couple of articles, quite a few that suggest, for example, the usage of graph databases. I guess, if I'm not wrong, Facebook is using the need for the database for recommendations.
I'm not a recommendations expert, so I'm really not qualified to answer answer your question properly, the example that I used is using is a technique called collaborative filtering, where you have this matrix. If you you can also do recommendations based on social signals, which, for example, Spotify does, and then something like Neo4j or something else might make sense. But that's a completely different technique for recommendations. And I honestly don't know anything about it. All right. Thank you very much.